project is accelerating Monte Carlo-based options pricing. My name is Ishita, and I work with Andrew, Angela, and Evan. So first we'll talk about the background and then dive into the implementation, as well as going over the different optimizations we made and our results and future work. So talking a little bit about the background, an options contract gives the holder the right to buy or sell an underlying asset at a specific price, which is known as a strike price, on or before a specific expiration date. So every options contract has a specific expiration date, which is denoted as T, and the holder must exercise the option if they want before or on this expiration date. The current market price of the asset of the underlying asset is represented by the stock price. This value is dynamic and changes as market conditions fluctuate. The strike price, which is also specified in the options contract, is the price at which the holder can buy or sell, buy in the case of a call option or sell in the case of a put option the asset. The black fork model is a mathematical model for pricing the options contract that we talked about previously. This model is based on the geometric Brownian motion, which with constant drift and velocity. It is, as seen on the slide, it is a second order differential equation, or second order partial differential equation that gives a theoretical estimate of the price of the options over time. S of t is the spot price of the asset at a specific time. D of t is the price of the option at that. The price of the option as a function of the underlying asset at time t. R is the risk-free interest rate, and then the v of the volatility, as well as the time. So by solving this equation for the corresponding boundary conditions, we have our solution gives us the price of the call option and the price of the put option. So in terms of how we actually simulated this, so the Monte Carlo methods can be used in finance to analyze the value of an option with multiple sources of uncertainty. So first, the price of the asset is simulated by a random number generation for a number of paths or trajectories. After repeatedly simulating the trajectories and computing the appropriate averages, the estimated price of the options can be obtained after converging a large amount of paths.
Okay, so next we'll talk more in detail about the algorithms that we used. So the main algorithm we used was the Monte Carlo algorithm for option pricing. We inputted a few parameters such as the stock and option price, as well as the expiration or the volatility, and we output the payoff price. To begin with, we initialize our random number generator with a seed, and then we iterate through the total number of simulations. For each simulation, we then generate random number and perform Box-Muller to find the Gaussian and then update the option status. And at the very end, we aggregate all of these results. We find the mean and calculate the option price and output that. And then we use the Gaussian Box-Muller algorithm to generate two Gaussian numbers. Basically, we used a random number generator to generate two random numbers, u and v, and we continuously generated that until they outputted u squared plus v squared, such that they're between 0 and 1. And then we calculate the two Gaussian numbers using the formulas shown on the screen. And then on to implementation. So here's a system level overview. We input our inputs to the algorithm using FIFOs, and we output them also using FIFOs to the Z board. The main pipeline of our design consists of the Box-Muller function and the update option status function, and we loop that for the total number of iterations. And then finally, we calculate the prices and output those. And we ended up achieving an II of 5. And then looking more into detail into our Gaussian number generator, overall, the Gaussian Box-Muller function implements the polar form of the Gaussian Box-Muller transform. Instead of using a while loop to calculate the two random numbers in between 0 and 1, we actually have a fixed loop iteration and preset u and v. And then as for the generate ran, instead of using a complicated algorithm like the one shown previously, we use a linear shift register to generate hardware efficient random numbers, and this ended up saving us some area and also only results in a 3% error instead of 1.5% compared to C++ ran.
So now talking about optimizations. One of the main optimizations that we required was pipelining. One of the big things about the Monte Carlo simulations is that each specific iteration is completely independent of the previous one. However, we didn't want to unroll the entire 1 million iterations, as this would require duplicating our area by 1 million times. So we settled on pipelining in this case, where we tried to achieve the same low II, but also try and save the same amount of area, but also create a fast iteration between each of our corresponding simulations. One of our big blockers is actually our II of 5, which is blocked by our floating point accumulation. On the pictures on the right, we have the call payoff sum as well as the put payoff sum, which are all bounded by the previous iteration. Given floating point accumulation, it does take around 4 to 5 cycles for this floating point accumulation to accumulate. Furthermore, in terms of what we have pipelined, we overall pipelined the entire simulation pipeline, where each specific simulation is pipelined where it's essentially split up between the Gaussian Box-Moller generation, then the various calculations for our zero, our call put, and then ultimately our accumulation with the call payoff sum. Furthermore, for our unrolling, we have unrolled the Gaussian Box-Moller, and within the Gaussian Box-Moller, like Angela previously mentioned, we have to generate our random numbers through our, and then also we've replaced our while loop with our for loop in this case to generate out our temporary u and v variables. Each of these variables needs to be unrolled and immediately generated in order to fulfill the pipelining constraints within our initial algorithm. The next couple of optimizations that we also want to create were inlining. Inlining is a really powerful tool that allowed us to incorporate interprocedural analysis for better optimizations. When we don't inline our specific random functions within our unrolled for loops, the tool can't identify what to optimize within that called function. As a result, by inlining these functions, we give the tool better analysis towards how to optimize away each of these random generations. Furthermore, we also determined our double versus floating point, and floating point actually turned out to be much cheaper in terms of area and latency, as we didn't need to get bottlenecked by our II, as well as allowed us to actually stay within our board's resource limits. Overall, we needed to save and used roughly 85% of the board simulation, which actually caused us to result in that II of 5. We did attempt to do dependency removal, where it artificially has a dependency array on the right. However, we weren't actually able to implement this fully, mainly due to the fact that our board area constraints were too high, and we repeatedly reached over the resource limit.
All right, so now on to some of the important results. So looking at the Zboard execution time, you can see that there's quite a large speed up between the baseline design and the fully optimized design. So going from the baseline design to pipeline design, you get about a 2x speed up. But when you combine pipelining, inlining, and loop unrolling, you get a fully optimized design that's about 225 times faster than the baseline design. So we thought that this was pretty promising results given our implementation. And also analyzing the resource usage a bit, you can see that some of the initial optimized designs, if we just implement pipelining or if we just implement inlining, have quite high latency. And the optimized design actually achieves the best latency by quite a few orders of magnitude. This does come at a trade-off, however, of using more flip-flops, more loops, etc., more DSPs. But we do think that this trade-off is well worth it, given the substantial speed-up we noted on the Zboard for the fully optimized design as compared to any of the other designs that we ran our simulations on. So now I'm going to go ahead and show a demo of this project on the Zboard. So first, just going to log into the Zboard. So I already have the FPGA programmed, and so I'm just going to go into the Zboard directory and run our simulation. So the compile times on the machine can be a little bit on the slow side, but it's not too bad. And there we have it. So the total time was 5220.044, and I believe that this design is a pipeline and inline design, but not the fully unrolled one, which is consistent with the data that we showed on the slides. And we got the correct expected call value and expected put value that we expected. And then now moving on to just some future work if we were to continue to work on this project in the future. So as Andrew noted earlier, our current II is 5, and ideally we get this down to 1 with further optimizations. We'd also like to try our simulation on more data, and that means that other options models could be involved in this, besides just selectuals, or also other types of options and how that kind of modifies our algorithms a bit. If we use like European versus American versus Asian options, for example. And then also optimizing even further, we could try different pseudo-random number generators. Since this was a pretty significant design bottleneck for us, we had to spend a lot of time getting Gaussian Box-Moller to work, but there are even more sophisticated cutting-edge BRNGs that we could use to optimize further. And that's our presentation. Thank you so much.
Thank you.